Good day to all of you listening to this presentation. First of all, I wish to thank the Combustion Institute, in particular Professor Tim Lewin and Professor Fei Kui, for giving me this opportunity to make this presentation. I wish to acknowledge my co-author, Vishnu R. Unni. Also, I wish to acknowledge the funding from the Department of Science and Technology, ONRG, and AFOSR. We know that practical flames often exhibit unsteady behavior. Studying unsteady flame dynamics is therefore very important to ensure the stable operation of combustion systems with increased efficiency and reduced pollution. I will now give an overview of the applications of dynamical systems theory and complex systems theory to study unsteady flames. I will focus on thermoacoustic instability and blow, but also discuss a few other topics briefly. Why do we need dynamic systems theory? Let's look at an unsteady flame. Thermoacoustics is indeed an acoustic phenomenon. So let's listen to a flame. We listen to the sound of a simple laminar flame inside a duct. As you can hear, these are periodic oscillations. That is, it's a limit cycle. Now let's listen to another one. You can't call this periodic. Turns out that this is chaos. Let's see what we can understand by applying the tools from dynamical systems theory. What is a dynamical system? A dynamical system is a system that evolves in time. One way to express it is using the set of ordinary differential equations dx by dt equal to f of x, where x is a vector that contains the variables that describe the state of the system. Dynamical systems often undergo bifurcation. What is a bifurcation? A bifurcation occurs when a small smooth change in parameter causes a sudden qualitative change in the behavior of the system. Thermoacoustic instability can be described as a half bifurcation. This bifurcation is characterized by the growth rate of oscillations changing sign from negative to positive. That is, we change from a system having a decay of oscillations to a system having a growth of oscillations as we change the control parameter. We have two types of half bifurcations, supercritical and subcritical bifurcations. In a supercritical half bifurcation, as we increase the control parameter, the system loses its stability and limit cycle oscillations are born. The amplitude of these limit cycle oscillations increase slowly as the control parameters increase past the half point. If we retrace the parameter variation back, the dynamical system retraces it way back just the way it came. In a subcritical half bifurcation, as we cross the bifurcation point, we see a jump in the amplitude of oscillations. When we retract the parameter, the system will not trace the original path. We need to retract the parameter value to a value significantly lower than the value at the half point for the system to return to its fixed point, that is the equilibrium point. This point where we go back to the fixed point is called the fold point. Such systems called bistable systems. This is the region of bistability. In the bistable region, if you perturb the system by a small disturbance within the basin of attraction of the fixed point, the system will decay to the fixed point. If the system is perturbed to an amplitude larger than the critical value, which is in the basin of attraction of the limit cycle, the system will evolve to a limit cycle. Such bistable systems show hysteresis. This is the bifurcation diagram of a diffusion flame. The location of the flame in the duct is the bifurcation parameter. As you can see, this system shows bistability and it also has hysteresis. If we are perturbing it with small amplitude disturbance, the system evolves to the fixed point, that is the thermoacoustically stable state. If we perturb the system above a critical amplitude, the system will evolve to the limit cycle. Dynamical system theory really took off in the 1960s. It is interesting to see that the combustion instability community could calculate the regions of bistability even before the term bistability was coined. The nonlinear dynamics work done by Croker and his students, Sirignano, Zinn, and Mitchell on triggering instability in the context of the F1 engine instability were really ahead of the times. However, in the subsequent decades, the focus in thermoacoustic instability was on solving it comprehensively using the linear theory. However, in the last decade, the focus has returned to the application of nonlinear dynamics in thermoacoustics. As I mentioned earlier, a dynamical system can be represented by a state vector. which contains all the state variables that define the system. We plot them in an n-dimensional geometrical space, a hyperspace, with each dimension corresponding to a state variable. Now, an engineer doing a CFD simulation will have access to all the state variables. However, experimentalist or an engineer in the field will probably have to live with just one transducer. So, can we reconstruct the phase space with just one measurement? Turns out that the answer is yes. Dynamical systems theory comes with a number of tools. We can reconstruct the phase space from a measured time series, that's just a single time series, using Takin's embedding theorem. We construct delayed vectors from the discrete time samples using an optimum time delay tau and an embedding dimension dE. The time delay is chosen as the first minimum of the plot of variation of average mutual information with time delay. To obtain the embedding dimension, we determine the false crossings of the trajectory with itself, which arise due to the projection of the system in a low dimensional space. We find the percentage of false neighbors created due to false crossings of trajectories while increasing the embedding dimension. At an appropriate embedding dimension, the percentage of false nearest neighbors will go to 0, and we'll choose this as our embedding dimension. We will now examine a simple experiment involving laminar flames. Our burner is a simple cap at the end of a tube of diameter 16 mm with 7 holes of 2 mm diameter each. The burner is surrounded by a 57 mm diameter glass duct. From the sound of the flame, we know that we have periodic oscillations, that is limit cycle oscillations. If you look at the FFT, it shows sharp peaks. The phase portraits both pressure and heat release rate through nice closed loops and the point gator sections, which are obtained by slicing the phase portrait by a plane shows discrete points. So this is limit cycle oscillations. If you listen carefully, you will observe that there is an amplitude modulation. The FFT shows multiple peaks having incommensurate frequencies. The phase portrait has a dense toroidal structure. A toroidal structure in phase space is an indication of quasi-periodic oscillations. The point gator section shows a closed curve, which is also indicative of quasi-periodic oscillations. As you would have listened, this bifurcation is even more interesting. The time series is definitely different, but nothing much can be said by just observing the time series. The power spectrum now has a broad band of frequencies instead of distinct peaks at characteristic frequencies, suggesting that this state is tending to a chaotic behavior. In the last slide, we saw a toroidal structure which now breaks down and forms an attractor with an irregular shape. This attractor is called a strange attractor as the trajectories do not follow a definite path. This can also be seen in the point gator section. The maximal Lyapunov exponent has a positive value. This indicates that this is definitely a chaotic behavior. There are indeed elaborate methods to characterize a chaotic attractor. We now have another state, a frequency lock state, where the trajectories of the attractor repeatedly return back to the initial point after many cycles. The power spectrum gets filled with distinct frequencies which are harmonics. This is called a frequency lock state. If you listen carefully, you will hear two frequencies. So here we observe two distinct peaks in the FFT, which are harmonics. The phase portrait shows two loops, which is characteristic of period 2 oscillations. In summary, we have a variety of signals, and these correspond to a variety of dynamical states. We have limit cycle oscillations, we have quasi-periodic oscillations, we have chaotic oscillations, and we have period 2 oscillations. The sequence of bifurcations we observed in our experiments is summarized in this figure. First, we go from steady state to limit cycle oscillations via half bifurcation, then from limit cycle oscillations to quasi-periodicity through a secondary half bifurcation, which is also called Niemark-Sarkar bifurcation. Then we go from quasi-periodic to chaos. This route to chaos is popularly known as the quasi-periodic route to chaos or the Royal-Takens scenario. As you can see in the first figure, during the limit cycle oscillations, flames undergo sinusoidal modulations. In the second figure, where we have quasi-periodic oscillations, the exact periodicity which was present in the case of limit cycle oscillations is absent. The loss of periodicity can also be seen in the flame shape modulations. In the last figure, we have chaotic oscillations. The chaotic nature of the oscillations is reflected in the flame images as well. We find that the flame exhibits irregular modulations. You can see the chaotic systems in the system are accompanied by rolling of the flame surface, as you see, for example, in figure D, lifting off in figures C and G, and elongation, as you see in figures B and E. Thus, flame dynamics is different for different dynamical states. As you can see, these are periodic oscillations. Contrast it with the intermittent oscillations that we're going to listen. Thus, we see that we can observe intermittency in thermoacoustic systems, and below is shown the time series. This is on the right, you have intermittent time series contrasted with the sinusoidal oscillations on the left side. So far, we discussed dynamical systems, but what about complexity? Let's take a look at this table from the book on Nonlinear Dynamics and Chaos by Strogatz. Here we have 4 quadrants, 2 axes. Top to bottom is nonlinearity, left to right is increasing the number of variables. On top left, we have things that we learned during our undergraduate classes. Linear systems such as dx over dt equal to minus kx, or a simple harmonic oscillator. As we increase the number of degrees of freedom to very large numbers, let's say Avogadro number, we get things like kinetic theory of gases, equilibrium statistical mechanics, etc. If we increase the number of degrees of freedom to infinity, we enter the realm of partial differential equations. We get things like the wave equation and heat equation. Now we look at the nonlinear regime, bottom left. With low degrees of freedom, we have things like fixed points for n equal to 1, nonlinear oscillations for n equal to 2, and we increase our degree of freedom to 3, we get chaos and fractals. You'll know that the framework also contains a region forbiddenly marked the frontier. These topics are not completely unexplored, of course, but it's fair to say that they lie at the current limits of understanding. The problems are very hard because they're both having large number of degrees of freedom and nonlinear. The resulting behavior is typically complicated in space and time, as the motion of a reacting turbulent fluid or the patterns of electrical activity in a fibrillating heart. Such systems are called complex systems. Let us now focus on the complex systems approach. A complex system is a system with multiple interacting components whose behavior cannot be simply inferred from the behavior of its components. Also, complex systems can self-organize. I'll show a video here in which we can see birds, and this birds are flying as a self-organized flock.
Huge flocks of synchronized starlings create beautiful sights of moving dark clouds. The phenomena was spotted in the skies of southern Israel on Saturday.
We know that it's the phase between the acoustic pressure and heat release rate that determines whether the acoustic energy is added to the system or absorbed from the system. First, let's take a look at the phase field in a turbulent combustor. Let's look at stable operation. The stable operation of a turbulent combustor is never really silent. We have low amplitude aperiodic oscillations called combustion noise. We can see that the instantaneous phase field is incoherent during stable operation. During the occurrence of thermoacoustic instability, the phase field is coherent. So the transition from stable operation to thermoacoustic instability is a transition from incoherent sound production to coherent sound production. The state of intermittency presages thermoacoustic instability, and we see instants when there is coherent sound production and also instants when there is incoherent sound production. The behavior of a thermoacoustic system, for example, arises from a variety of factors such as molecular mixing, turbulent transport that involves a wide range of scales, chemical kinetics, acoustic wave interactions, etc., giving rise to the possibility of chaotic fluctuations on one hand and ordered periodic oscillations on the other hand. A turbulent reacting flow field is thus indeed a complex system. A high level of coherence is observed during thermoacoustic instability. Often engineers and technicians refer to such coherent thermoacoustic system as something that is alive, even using terminology such as the combuster's breathing. Large coherent structures emerge in the turbulent flow during the occurrence of thermoacoustic instability. Such emergent behavior is a telltale sign of complex systems. The self-organization of the turbulent flow and the emergence of the ordered acoustic field and large coherent structures happen by itself. In summary, we can view thermoacoustic instability in turbulent combustors as order emerging from chaos in a complex system. In a reductionist approach, we zoom into the constituent elements of a system and analyze them in detail. In a complex system approach, we do not split things apart and zoom in on the component behavior. On the contrary, in a complex system approach, the focus is on the interaction between the constituent elements. We focus on the new phenomena that can emerge from a simple set of components interacting through a simple set of rules. The key ingredients of complex systems are interacting elements, nonlinear feedback that affects the behavior of the systems, and exchange of energy and mass with surroundings. A thermoacoustic system that involves turbulent reacting flow has all these ingredients. Complex systems show emergent properties. What is emergence? Let me give an example. We cannot explain the wetness of water by examining the individual molecules of H2O and their properties. It's an emergent property that originates from the interaction of the H2O molecules. From a reductionist and linear perspective, emergent phenomena are often surprising. Having discussed the basics of complex systems theory, let us now examine the thermoacoustic transition in a turbulent combustor. The stable operation of a turbulent combustor is never really silent. Let's now listen to the sound. We have low amplitude aperiodic oscillations called combustion noise. It has a Gaussian distribution and has traditionally been treated as stochastic. Recently, we have shown that combustion noise is actually deterministic chaos. Here is the signal during combustion instability, and on this right side of this plot is the zoomed version. You can see it's clean periodic oscillations. Let's listen to the sound for a moment. Recently, we have shown that intermittency presages thermoacoustic instability. During intermittency, we see bursts of periodic oscillations amidst epochs of aperiodic oscillations. Listen carefully. So we can replace the stable to unstable paradigm with chaos through intermittency to limit cycle. Dynamical systems theory and complex systems theory comes with a number of tools. Recurrence plot is a graphical way of representing the system dynamics of a time series in 2 dimensions. We first construct the phase portrait from the time series data. Then we plot the recurrence plot. We have time and time on both the axes. And we first start with a point in the phase portrait. We have an epsilon ball around a particular point. Then we see if the trajectory returns next time into the ball, we put a black dot. If the trajectory does not recur inside the inside this epsilon ball, we put a white dot. In summary, recurrence plots gives patterns, and we human beings are very good at recognizing patterns. Limit cycle appears as equally spaced diagonal lines as shown on the picture on the left. Quasi-periodic oscillations appear as diagonal line segments that have unequal spacing, a manifestation of the incommensurate frequencies. You can see this on the picture on the right. Recurrence plot of an intermittent signal has black patches. When the trajectory is in the low amplitude regime, it will stay in the black patch. When the trajectory jumps out of the epsilon ball, we get white. Thus, the transition from combustion noise to thermoacoustic instability via intermittency can be represented in terms of recurrence plot shown here. Recurrence plots can be quantified using measures such as recurrence rate, which is the density of black points in the plot, or entropy of the signal, or the trapping time, that is, the time when the signal is trapped in the low amplitude regimes. These measures can be used to determine the proximity of the system to the onset of thermoacoustic instability and hence used as precursors. Thermoacoustic instability is the result of interaction between hydrodynamic, combustion, and acoustic subsystems of a combustor. The mutual interaction between these subsystems leads to self-organization and the emergence of patterns, that is, the acoustic field and the large coherent structures in the system. This interaction can be studied using the framework of synchronization theory. During combustion noise, we have chaotic oscillations that are desynchronized. You can see on the top left. Now on top right, you can see during intermittency, we observe intermittent phase synchronization. Also, it is interesting to note that the signals are desynchronized during the aperiodic part, whereas they are synchronized during the periodic part. Then we see a state where the signals are periodic and their phases are synchronized. This is called phase synchronization. Then we see a state on bottom right where we see that both the amplitudes and phases are logged, and one signal can be written as a function of the other signal. This is called generalized synchronization. Note that phase synchronization is associated with low amplitude instability, and generalized synchronization is associated with a high amplitude instability. In summary, we go from desynchronized chaos to intermittent phase synchronization to phase synchronization and finally generalized synchronization. We now want to examine the spatiotemporal dynamics. We'll look at the phase angle between the acoustic pressure oscillations and the heat release rate oscillations. The phase field is incoherent during the occurrence of combustion noise. It's coherent during thermoacoustic instability. During intermittency, you can see that the phase field is coherent during the periodic burst and incoherent during the periodic epochs. We then represent the phasors using arrows. We see that during the occurrence of combustion noise, the phasors are not aligned. That is, they are aligned randomly. During thermoacoustic instability, the phasors are indeed aligned. The emergence of order from disorder happens through a chimera state where order and disorder coexist simultaneously, that is during the state of intermittency. This is a classical feature of complex systems that shows a mix of ordered and disordered behaviors. The spatiotemporal state that we observe in our system during intermittency is a chimera state, where order coexists with disorder. Chimera is named after the Greek mythological monster, which has a lion's head, a goat's body, and a serpent's tail. The regions of disordered and ordered phases change their locations with time. Such a state is called a breathing chimera state. Next, we examine how we can use tools from fractals and multifractals to study combustion instability. A chaotic time series has a self-similar structure with patterns that fill non-integer dimensions. If we examine the combustion noise signal, we see that the signal appears to be self-similar. In other words, the signal has fractal characteristics. The Hurst exponent describes how the RMS of the standard deviation of fluctuations scales with the time over which it is calculated following a power law. We split the signal into segments and then plot on a log-log plot the RMS of standard deviation of fluctuations as a function of the time scale over which it is calculated. The slope of this plot gives the Hurst exponent. As we approach an impending instability, we see that the Hurst exponent approaches zero smoothly. On the left, we have a sole combustor, and on the right, we have a bluff body combustor. The RMS in the beginning hardly changes. However, during the state, we can see that the Hurst exponent is falling rapidly. Thus, the Hurst exponent can be used as a precursor to the onset of thermoacoustic instability. The signals are complex and are represented by an array of scaling, or an array of Hurst exponents, which can be represented compactly as a spectrum of singularities in the multifractal spectrum. I'm not going over the details here, but we can see that as we approach an impending instability, we see that the Hurst exponent is approaching zero, and also there is a loss of multifractality. Next, we look at complex networks. Complex network analysis is an appropriate framework to study complex systems such as thermoacoustic systems. In a complex network, we have nodes that are connected by edges. We recently introduced complex network analysis to the study of thermoacoustic instability. We studied the patterns in the time series of unsteady pressure as a combustor approached thermoacoustic instability by constructing visibility networks corresponding to pressure fluctuations during the different stages of combustor operation. Each local peak in the time series is considered as a node in the complex network. Two nodes are connected if the peaks can be connected with a straight line that does not intersect any other peak in between. We will now use this visibility algorithm to characterize time series from thermoacoustic systems. First, we'll characterize combustion noise. We find that combustion noise can be represented as a scale-free network. That is, the fraction of nodes having k number of connections follows a power law with the number of connections k. That is, P of k, the probability that a node has k connection, is proportional to k power minus gamma. Scale-free networks are ubiquitous. We can see them in many networks such as World Wide Web, airline networks, scientific collaboration networks, biological networks, etc. Further, we observe that during the transition from combustion noise to thermoacoustic instability, that is when we go from stable operation to unstable operation, we see that the scale-free network transitions to a regular network. Similarly, we can construct recurrence networks. In the phase space, if the trajectories are recurring, we connect the states. Recurrence networks have been used to study thermoacoustic transitions. In the slide, we show the transition from combustion noise through intermittency to thermoacoustic instability and through intermittency to blowout. There are measures based on statistical mechanics of complex networks. These measures can be used to quantify the proximity to thermoacoustic instability and blowout. Complex networks can be used to characterize the spatiotemporal dynamics of a thermoacoustic system. We can identify the critical nodes of the network responsible for the establishment of global connectivity in the network and hence the emergence of thermoacoustic instability. This is indeed a smart way of implementing passive control. Here we perform PIV, particle image velocimetry, on a bluff body combustor and obtain the velocity vector field in a grid of points in the reactive flow field and use this data to construct spatially weighted correlation network. We construct a network by correlating the velocity field at two different locations. We connect the nodes if the correlation coefficient is greater than or equal to 0.5. The correlation coefficient is the weight of the edge, that is the connection. We estimated the strength of a node, local clustering coefficient, and closeness centrality in order to identify the critical region in the reaction field. In the critical region, the values of this network measures are high. The strength of the node is given by the sum of its weights. Clustering coefficient measures the ratio of the number of connected pairs of neighbors of a node to the total number of connections possible between these neighbors. Closeness centrality quantifies the average shortest distance of a node with all other nodes in a network. We can express closeness centrality as the normalized inverse of the sum of the shortest paths between node and rest of the nodes. We observe very high values of node strength only during thermoacoustic instability, near the backward facing step above the bluff body shaft. This region also has very high clustering coefficient, as you can see in the second row. Hence, we can say that the velocity variations in this region are highly correlated among themselves when thermoacoustic instability occurs. In other words, the region near the backward facing step above the bluff body shaft is spatially coherent regarding the velocity variation. High values of this network measures are due to the periodic coherent motion of the flow at the combustor inlet, which eventually self-organizes to form large-scale coherent structures during thermoacoustic instability. Also, we see that the above-mentioned region has high values of closeness centrality. Hence, we can infer that any perturbation given to this region above the bluff body shaft will reach all other parts of the flow field quickly. From the high values of spatial distribution of these network measures, we find that the region downstream of the backward facing step on top of the bluff body shaft emerges as the most critical region during the onset of thermoacoustic instability. Thus, we can hypothesize that any passive control strategies could be directed at this critical region to mitigate thermoacoustic oscillations. Usually, passive control is implemented by trial and error. This is indeed an expensive process. Instead, a smart passive control methodology can be implemented where we identify the critical region in the reacting flow field and disturb the flow field in this region, for example, using microjets. We identified a region inside the bluff body combustor as the critical region, and we perturb the flow in this region by injecting microjets. As a result, thermoacoustic instability is suppressed above a critical value of the momentum flux of the microjets. We showed that the critical region identified through this network analysis is the most effective location in suppressing thermoacoustic instability through microjet injection. We can see that with the introduction of microjets, the critical locations no longer remain to be hubs in the network. As a result, thermoacoustic instability is suppressed. We see that the size of the giant cluster of positive acoustic power production decreases with microjet injections. Thus, thermoacoustic oscillations are suppressed when coherent acoustic power production over large clusters ceases. Now let's take a look at flame blowout. Flame stabilization inside a combustor is a challenging problem since the flow rates and the local velocities inside the combustor are often very high. Hence, flow modifiers such as swirler or bluff body are provided along the flow path in order to create recirculation regions inside the reactive flow where a flame can be stabilized. While such flame stabilization mechanisms are designed to ensure the establishment of stable flame for a wide operational envelope, under some conditions flames fail to anchor inside the combustor and can be blown out of the combustor. Blowout is traditionally seen as a loss of static stability of the flame. Now we see that blowout is a dynamically rich process. There's a lot of unsteadiness. Now the flame, you can see it's moving away from the flame holder and it eventually comes back. So there's a lot of complexity as illustrated in this movie. We will examine flame blowout in a simple laminar flow setup with the duct around a Bunsen burner type flame. We first have limit cycle oscillations. Then we can identify two more regimes from this bifurcation diagram before the flame blows out. Let's now use the tools from dynamical systems theory to dig deeper. We observe a half bifurcation and a secondary half bifurcation and subsequently intermittency. As we go through the half bifurcation, the thermoacoustic system displays limit cycle oscillations. At the secondary half bifurcation, we see the emergence of quasi-periodicity. Eventually, we get intermittency, where the trajectory switches between regular and irregular oscillations. This intermittency is a precursor to blowout. Earlier, we talked about getting recurrence plots. The patterns in these recurrence plots, particularly the kite-like structures, indicate type 2 intermittency. A sequence of flame images acquired during intermittency by a video camera and instantaneous high-speed images acquired by a high-speed camera are shown here. The images correspond to flame oscillation prior to liftoff, during liftoff, and during reattachment. The video images give an estimate of the amplitude of flame oscillations and the mean flame shape during its different stages. And the instantaneous images give an idea of the degree of stretching and folding the flame undergoes. Oscillations in the flame surface prior to the burst phase, while it is still attached to the burner rim, is similar to limit cycle oscillations. During the high amplitude burst, flame gets detached from the rim and lifts off. During these oscillations, we observe extreme folding and stretching. Please see this flame image marked by a red dashed circle and even local short time extinction as seen by the flame image marked with a red solid circle. Reattachment occurs simultaneously with the end of the burst phase. You can see in images P to R that the flame is reattaching. Following this, a steady state exists for a very short time. Image frame R is the reattached flame with no oscillations, resulting in a sharp image. The oscillations reappear in the flame and in the acoustic pressure, leading to another burst phase, and this entire behavior repeats at regular time intervals. Gradually, as the flame location is varied, the bursts become more frequent, and eventually the flame is unable to sustain a stable attachment with the burner, causing blowout. Now let's examine blowout in turbulent combustors. These are results from a very nice paper by Nair and Duivin, which show that in turbulent combustors, flame blowout happens through multiple stages. The first stage of flame blowout is marked by localized extinction along the flame sheet, namely the formation of flame holes, their convection along the flame, and their subsequent healing towards a continuous flame surface. Although the stage acts as a marker towards flame blowout, it has been suggested that the flame can survive indefinitely in this stage. As the flame approaches blowout, we find a significant increase in intermittent events and observe low frequency acoustic emission. The second stage corresponds to a collective flame extinction. This collective extinction within the shear layers may be the ultimate cause of blowout. These events provide an acoustic signature prior to blowout. The tools from complex system theory can be used to automate the detection of an impending blowout and quantify the proximity to blowout. We can construct the phase space using the time series of acoustic fluctuations. Measures that quantify phase space serve as precursors to flame blowout. Gotoda and co-workers use translation error, which quantifies the degree of parallelism of trajectories in the phase space as a control variable to prevent lean blowout. Gotoda and co-workers, in a series of breakthrough papers, characterized complexities in combustion instability and blowout in a lean premixed gas turbine motor combustor by nonlinear time series analysis to evaluate permutation entropy, fractal dimensions, and short-term predictability. The dynamic behavior in combustion instability near lean blowout exhibits a self-affine structure and is ascribed to fractional Brownian motion. Gotoda's group also showed that the phase space close to blowout exhibits multifractal behavior. They used many other measures based on phase space to detect significant changes in the combustion state at low equivalence ratio. Recently, there has been a surge in interest in the application of machine learning to study combustion dynamics. As an example, in this work, Professor Ray's group at Penn State uses hidden Markov modeling to detect flame blowout. Recently, Gotoda's group has used machine learning in combination with complex networks to study combustion dynamics. We can describe both thermoacoustic instability and blowout in the framework of multifractal analysis. In this figure, we can see that as the system approaches thermoacoustic instability, the Hertz exponent decreases. And as we proceed towards blowout, the Hertz exponent increases to higher values. Similarly, the multifractal spectrum shrinks as we approach thermoacoustic instability, and then it expands further as we approach blowout. Blowout is the result of local interaction between the flow and the flame, leading to global extinction of the flame. Flame front and convecting Kelvin-Helmholtz vortices along the shear layer overlap to induce high local strain or hydrodynamic stretch rates that exceed the corresponding extinction stretch rates, resulting in local flame extinction along the shear layers. Fresh reactants entrain through shear layers to react within the recirculation zone due to favorable residence time there. This flame kernel within the recirculation zone may survive several milliseconds and reignite the shear layers, such that the entire flame is re-established temporarily. We observe repeated extinction and reignition before final blow-off when the flame kernel fails to reignite. Thus, the local extinction occurring at locations in the shear layer trigger a collective flamelet extinction event. We now discuss the cellular automata based on population dynamics to model blowout. A turbulent flame can be considered as a collection of large number of flamelets. The population dynamics of these flamelets could be used to model the overall flame behavior as a contact process. In this context, flame blowout can be viewed as the population of flamelets approaching zero. In other words, extinction of flamelets. To construct the cellular automaton, first we divide the reaction field inside the combustor into a uniform square grid. The value assigned to each cell of the grid represents the state of the reactive flow in the corresponding spatial location. The states can be unburned, denoted by 0, burning, denoted by 1, or burnt, denoted by 2. The cell in a burning state represents a flamelet. In each step of cellular automata, each cell interacts with their neighboring cells, following a set of rules. The local interaction between the flowing fluid particles which are unburnt, burning, or burnt leads to the propagation of the flame in the flow field. In each step of flame propagation, a burnt site would remain burnt, that is 2 remains 2, and a burning site will become burnt, that is 1 becomes 2. An unburned site would burn with a probability P if there is at least one site in its Moore neighborhood, that is the 8 sites which surround it, which is burning. Here, P is the probability of flame propagation. When the probability of flame propagation P reduces, the average flame speed reduces. At lean equivalence ratios close to blowout, the flame speed reduces when the equivalence ratio of the combustible mixture reduces. Thus, reducing P is equivalent to reducing the equivalence ratio of the combustion and approaching lean blowout. The mean flow is simulated here by translating the window of computation. If the number of burning fluid particles in the reacting field goes below n, no burning parcels are added on top and bottom of the block body, and hence the flame is no longer anchored at the burner. In the study, I think we used N as 3. This corresponds to a situation when the flame blade fails to sustain the chain reaction, eventually leading to flame blowout. As the probability of reignition reduces, we approach flame blowout. This is a movie from the simulations. We can see as we approach flame blowout, flame stretches and becomes parallel to the flow. The number of flame holes increases. Eventually, beyond the threshold value of P, the flame blows out. Qualitatively, the results from the model show similarities with the experimental results. Variance of fluctuations reduces close to blowout. There is increased low frequency content at low equivalence ratios. Thus, blowout is similar to a threshold-like absorbing phase transition. As the probability of flame propagation P reduces, the average density of population of flamelets reduces. Beyond the threshold value of P, the population density goes to 0, indicating an extinction of flamelets. In recent years, there has been a strong interest in the application of dynamical systems theory and complex systems theory to study the dynamics of IC engines. I will only list out a small sample here. Daw et al. Showed that cyclic variability in IC engines can be modeled using nonlinear stochastic framework. Sen et al. Showed that wavelet transform and multifractal analysis shows presence of long timescale non-stochastic oscillations in cyclic variability. The deterministic nature of dynamics will become increasingly significant in designing control strategies to meet the aggressive emission standards, and a good review paper is the one by Finney et al. And as in the other fields, data-driven feedback methods have become very popular, and they have been used to control knocking in IC engines. Studying flame flow interaction is essential to understand combustion. Tools from nonlinear dynamics and complex systems theory are very useful in characterizing both the evolution of the topology of the flame and the interaction between the flame and flow. Visibility networks can characterize flame topology. Clusters of high degrees are found in folded regions in the flame front. Hubs emerge due to the turbulence flame interaction in the folded regions. Folded regions lead to self-intersection towards reactant island formation and eventually annihilation, causing large fluctuations in turbulent flame speed. Complex networks provide new ways to study statistics of turbulent flames. The significance of the time scale of turbulence flame interaction was uncovered using network analysis. Wang et al. Showed that this time scale is as important as turbulence intensity in determining the dynamics of a turbulent flame. Spreading a forest fire has been modeled using cellular automata. Spatial distribution of fire breaks is reduced to the problem of finding the group of nodes through which the fire spreads most rapidly. Network centrality measures have been used to determine the optimal locations for fire breaks. Complex network measures can be used for model reduction for chemical reactions. Shao et al. Showed that the between the centrality concept could properly rank the importance of the species. They demonstrated that skeletal mechanisms can be generated quite flexibly by this between the centrality ranking and can capture the detailed kinetics of important intermediates. In summary, nonlinear dynamics and complex system theory provides frameworks to analyze data, predict and control dynamics, and model unsteady combustion. Recent efforts to apply bifurcation theory, synchronization theory, fractals, and complex networks to problems in unsteady combustion have yielded rich dividends in obtaining insights for problems such as thermoacoustic instability, blowout, dynamics of IC engine combustion, spreading of forest fire. Nevertheless, these efforts have been scattered across different domains and are often specific adaptations to specific problems. We need to develop a comprehensive and unified framework based on tools from nonlinear dynamics and complex system theory to study unsteady combustion. This cartoon from Jacobello et al. Illustrates some of the applications of complex system theory. Improving our understanding and control of unsteady combustion will require the application of latest advances in complex systems theory. Researchers in laser diagnostics and researchers in LES need to work together with researchers in complex system theory, transcending the boundaries between engineering, physics, and mathematics. Dynamical systems theory and complex system theory allows us to analyze unsteady reacting flows from a new perspective. Connectivity in turbulent reacting flows are abstract. Complex system theory helps us analyze these hidden connectivities in the flow. It helps us to unravel patterns and map mutual interaction between flow and other subsystems. It helps us to study causal relationships between the subsystems. It provides us with new statistics that describe turbulent flows. It aids model reduction for flow and reaction. It helps us to identify critical regions in a flow, and it helps us to implement smart control methodologies for reacting flows. Deep learning in conjunction with network analysis will be a powerful tool in analyzing, prognosing, and controlling reacting flows. Complex network framework provides abstract representation of flows, and machine learning methodologies can identify patterns in these networks and learn to predict the evolution of these patterns. Let us look at the table of process Strogatz one more time. Let us zoom in on the region forbiddingly marked the frontier. It reminds me of those old maps of the world where the map makers wrote, "Here be dragons," on the unexplored parts of the globe. These topics are not completely unexplored, but of course it is reasonable to say that they lie at the limits of current understanding. Turbulent reacting flows definitely figure in this list. These problems are hard because they are both large and nonlinear. Unsteady combustion is the height of spatio-temporal complexity. Complex systems theory itself needs to be advanced to accommodate the complexities of turbulent reacting flow. This indeed is an exciting prospect. Thank you.